All right, this is AP Calculus BC Lesson 4-6, Integration by Parts. There are 2 homework assignments tonight, and I'm giving you 1 day each to do the homeworks, which means if the lesson is today, Monday, Tuesday you're working on the first homework, Wednesday you're working on the second homework, and we'll have a new lesson on Thursday. Our objective today is to use integration by parts on both indefinite and definite integrals. So where does integration by parts come from? A better way of thinking about integration by parts is it's just the backwards product rule. What do I mean by that? So if I have 2 functions, let's talk about product rule. 1 times 2, we all know the standard formula. You could probably shout at your computer right now. It's 1d2 plus 2d1. Let's undo that. So what I'm going to do is I'm going to take the antiderivative, the integral of this 1 times 2, and that's still taking the derivative. I'm being super informal here. I'm not writing dx or anything like that. And therefore, I'm going to be taking the integral of 1 d2, and I'm going to take the integral of 2 d1. I'm just kind of universally applying the integral here. And then if I take the antiderivative of the derivative, those 2 cancel each other out, and I'm just left with 1 times 2 with no derivative. And that's it. That's all I'm going to do. I could rewrite this, I guess. 1 d2 plus the integral of 2 d1, but that's in essence what it is. They rearrange some things to actually make it useful. So one thing that is useful is like getting one of these integrals by itself. So I don't know, let's randomly choose that one, I guess. So let's subtract this integral of 1 d2 from both sides minus this 1, or minus the integral, minus the integral of 1 d2 from both sides, and I'm left with, I'm also going to switch these sides, so I'm going to say that this is now my left-hand side, because this is what it looks like in textbooks. So you'll say the integral of 2 d1 is equal to 1 times 2, not 12, just 1 times 2, and then minus this integral of 1 d2, and that is your integration by parts. More typically it's written a little bit different, I guess, in textbooks. Instead of 2 and 1, they usually use u and v. Alright, so let's say this 1, let's change it to a v. So let's say that's v and that's u. So 2 turns into, this is going to be the integral of u, and then d1 is dv. This is equal to 1 times 2. And I guess we could write v and u, but I think in the textbook it's u times v. I guess we can switch those around. Minus the integral of 1 is v, and d2 is du. And this is just a formula that you're going to have to memorize. Maybe if you don't memorize it, you can just memorize the pattern. So I'll maybe put a star here. Memorize that one. This is the formula with indefinite. In order to make it definite, it's pretty straightforward, so let's go ahead and just do that in a different color. If it was definite, like between a and b, instead of no bounds of u dv, that's supposed to be a v, by the way. I know that my v's need to be sharper. That's just u v evaluation bar between a and b minus the integral from a to b of that v du. So it's just adding on those bounds. It's not too tricky. The hardest part about using integration by parts is applying the formula. Like, yes, it's easy to memorize a formula. Yes, it's easy to memorize a second formula. It's a slight twist of it. But how do you choose your u and how do you choose your dv? So essentially, every problem that I'm going to be giving you, you need to somehow get these symbols and choose which one is your u, which one is your dv. That's your first step and your hardest step. Generally speaking, in all of AP Calculus, there's only 2 ways to do it. So if you get it wrong the first time, you do it the other way and you get it correct. It's just a little bit annoying. The more and more you do these problems, the better you'll do. So again, I need to write this as, I need a u and I need a dv. So I have to figure out those 2 values and then know that if I have a u, eventually I'm going to be taking its derivative. Look over in our formula. If I have a u, then I have a u, good. Okay, eventually I need a du. I need to eventually take its derivative. So down here in a second color, I know that eventually I'm going to need a du. Same thing for the v. If I choose a dv, eventually I'm going to have to go backwards to get a v, which means I have to take the antiderivative. So I'm just going to write v here and know that to get from here, this dv to v, I'm taking the antiderivative, and to get from the u to the du, I'm taking the derivative, so something prime. So I'm going forwards and I'm going backwards. And then choosing values based on that information is generally the whole trick here. So which value is really good for taking derivatives? What's a nice value? And the answer is, well, if I take x, the derivative of x is 1. 1 is a nice value. I like du set equal to 1. So therefore, I'm going to say u, let's set that equal to x, and therefore du is 1. Well, if u is x, then this other piece here, this e to the 6x, must be dv. So that's what I'll say here, e to the power of 6x. And as a general rule of thumb, e can really go in either of these spots. It typically works better in dv. You'll see why in a bit. And then if I take the antiderivative of e house is just e house, so e to the 6x. Notice I'm giving some space in front of here because I had to use taxman. I'm doing taxman in my head, and I know in order to pay taxman, I need to pay taxman with a rate of 1/6. And if you can't think of why to do that, remember if I do the derivative of the inner, the derivative of 6x, if I was going forwards, I would have to multiply by 6. So if I'm going backwards, I would have to divide by 6. And you can write out taxman on the side too if that's confusing you, but I'm hoping by now, well, maybe not by now because I know this is right after the break, but hopefully by this point in your calculus career, you've done taxman so many times that these problems become straightforward. But for the sake of just doing it, I'll do it once and then never again, right? So we need a u, we need a taxman, and we need a u prime. We're saying our u is 6x, our taxman is 1, we don't know, and the derivative of u is 6, and I'm paying 1/6. Okay, never again, there it is. Let's actually use this formula now. So I already have u dv. I've written this part right here. It's already listed for us. I now need to write this right-hand piece, and then I'm basically done as long as I evaluate what that is. So I now say this is equal to, I'll just come down here, I'll say that this antiderivative of x e to the 6x dx is equal to u times v. And then this is kind of the pattern. U times v, as long as you list u and then dv, it's always going to be this diagonal from the top left to the bottom right. So it's x times this 1/6 e to the power of 6x. And that's going to be x over 6 e to the 6x. So I just wrote u times v. Now I'm going to subtract the integral of v du. So subtract the integral of this v du and v du, that's v du, and then the last two that I need to multiply are these two. So it kind of goes diagonally and then the bottom, which means this dv we never use, and you'll see in here, while dv is originally listed, you never actually use it when you're writing out the equation. So v du is just, since du is 1, it's just v. It's 1/6 e to the 6x dx. So technically, we actually have the dx right here, because when I take the antiderivative, the dx goes away. Remember, we take the antiderivative of the dx, and then that goes away. So whenever we do this process of taking the antiderivative, it should go away. And therefore, when I have x, this turns into a dx down there. So they do still happen to be formal about it. Okay, so we're basically done. Now we actually have to evaluate what is the antiderivative of this, and we know that we can do that. Before we couldn't do that because we had an x in front of this, and taxman would break down. But from here, it's pretty straightforward. So again, it's taxman. I'm going to divide by 6 yet again. And my final answer, I can write this in a different color. I'm still going to write this x over 6 e to the 6x minus, okay, antiderivative is now 1 over 36. I'm dividing by 6 again, e to the 6x, and don't forget your cake, your plus c. And there's our final answer. We'll box it. After solving that, I kind of realized, like, why did you even know to use this integration by parts to begin with? And it's kind of your last resort when taxman doesn't work. I taught a few tricks on how to get around problems involving when taxman doesn't work, but this is like the one true method that will always work. Let's actually go back a step, and this is where you just gotta kind of listen, and you don't have to take notes on this, but the general idea is when taxman fails, use this. So let's go ahead and show where it breaks down. So if I was trying to do the integral of x e to the 6x dx, let's go ahead and use taxman. So u, I would say that's probably equal to the 6x. I would say taxman, he's out front, taxman is x. U prime is equal to 6. And then I would say, okay, you're going to pay taxman x over 6, and oh gosh, that's just x over 6. You're paying taxman a variable rate, and we're not allowed to pay taxman a variable rate And there's no tricks that you can do here. It's not like, oh, just distribute that square root or anything like that. So we're stuck, and this doesn't work. So I'll say doesn't work. Doesn't work. And therefore you have to use a new method, the one that I'm teaching today. Let's move on to another example, example number 2. It looks kind of similar. I have x times some other function, and it also is similar in its solution. You have enough now to solve this on your own if you want to give it a shot. If you really want to test your skills, please pause the video. I know that a lot of us don't, though. So again, set it up. U and dv. We need to figure out what each of those are, and I need to give myself more room. I realized the last problem was kind of condensed together. So dv. All right. And then from there, I know that u is eventually going to turn into du, I'll take its derivative, and dv is going to turn into v, I'll take its antiderivative. What are good values to choose such that I can take the derivative really nicely? Well, the derivative of x is really nice. The derivative of x is 1. And I'm not going to write any dx in here because it's just kind of, I don't know, too much extra work. I already know where they're going to go. dv, that has to be the other one, cosine of x. Let's see, does cosine of x, the antiderivative of cosine, so anti-c, anti-change is same, so it's going to be the same sign, so it's going to be positive still, and it's going to be positive sine of x. We don't have to worry about taxman or anything because x, the derivative of x is 1, so it's directly just sine. And then we just plug it into the formula. Again, the pattern that you should memorize once you have this set up is you're going to multiply these two together and then subtract the integral of that one. So yeah, first, these two. So this is going to be equal to x sine of x minus the integral of these two. And I guess I should choose that integral to be a different color. And then these two. So it's going to be the integral of 1 times sine of x, or just sine of x. And to make this look a little bit formal, slap on a dx right there, and I'm basically done. I just now need to, I don't know, I said that, why? I basically now need to take the antiderivative of that sine of x, and I'm done. So I'm going to rewrite this x sine of x, nothing changed there, minus, okay, antiderivative of sine, anti-s, anti-same is changed, so it's now going to change signs from a positive to a negative, ooh, double negatives here, and cosine of x. And all I've got to do to make this formal is do plus plus, and don't forget my plus c. I guess I can just totally ignore that one, and there's my final answer. Box it. I realize now also I'm not talking about how do you know if it failed. Well, if you are taking, if you keep getting a problem that you can't solve, an integral that you keep applying this rule, this integration by parts over and over and over again, after the third time, you've probably done it wrong. And for AP Calculus, if you've done it twice, don't quote me on that, because I know that there, in college I saw a lot of professors love to throw integration by parts at least twice, and you had to do it. And then it like solved magically on that second go about. But I've never seen it go 3 times. Example number 3, again, it's another indefinite. Finally, we'll get a definite in example 4, and I don't want to do too many because getting the math to come out nicely for them can be tricky. I know in Khan Academy sometimes they come out really gross with like really big fractions. Oh, okay, so this one looks a lot different. Example number 3 doesn't have any like, there's no 2 parts, right? And the reverse product rule basically states that you have 2 things being multiplied together. I only see 1 thing here, so why do I need integration by parts on this one? Well, I know how to take the derivative of arctan. I don't know how to take its antiderivative. It's kind of like the same problem of I know how to take the derivative of natural log, but I don't know how to take the antiderivative of natural log. They're like those special rules that kind of only work one way, so I think that's the reason why we have to use it here. There's no u substitution that I can do. Maybe I can turn that into sine, cosine. No, okay, so go ahead and just set this up again. U is equal to that, dv is equal to that. And then, yeah, of course, u is going to turn into du, I'll take its derivative, and v is going to turn into v, I'll take its antiderivative. What do we got here for u? Well, I just said it's really easy to take the derivative of arctangent, so this is taking the derivative on the u, this is taking the antiderivative. So let's go ahead and plug in arctangent into the u. We'll say this is going to be arctangent to -1 of x, and what's left over? Nothing. It's just 1. You can technically say this is actually dx if you're being super formal about it, but I never am, and I don't think you should be unless you're showing your work or something. That's just 1. It's nothing. Alright, so let's go ahead and take that derivative, and again, do you remember your derivatives of your arc trig? Do you remember antiderivative of arcsine, arccosine, arctangent. Well, I know the one for arctangent pretty well. It's 1 over, it's not 1 minus anything, it's 1 plus x squared. And as a note, if they show up, I haven't looked too closely at the homework, but say you have arcsine of x, the derivative, so dx of arcsine of x, let's see if I can even remember it, is equal to 1 over, oh, it's actually negative for sine, isn't it? Is it negative for sine or negative for cosine? Ooh, I forgot. I'm going to guess it's positive. I'll look it up in a sec. Square root of 1 minus x squared. I did look it up off camera, and I am correct, which means the derivative with respect to x of arccosine is the other one. That's equal to the negative 1 over the square root of 1 minus x squared. And wow, I did not do this correct, did I? No. Okay, so this should be a 1 plus x squared. Whew, okay, caught that mistake. And then from there, oh yeah, let's go diagonally down here. So this is going to be equal to, and hold on, let me change to black real quick. So in terms of the black direction, it's going to be x times arctangent of x, and then minus, and it's going to be the integral of this red direction here. So minus the integral of x over 1 plus x squared dx, and that one can be solved. That's we're gonna have to use Taxman for that one, but Taxman will actually work. It doesn't work for that one, but it works for this one. Let's go through Taxman once again. Just know that my u is going to be 1 plus x squared, so I'm going to pay Taxman. I said I wouldn't do it again. I'm doing it again, aren't I? U prime is 2x, Taxman is x, so I'm paying Taxman 1/2. So coming back to my original problem, this is really going to be minus 1/2 1 over x squared, so it's going to be natural log of 1 plus x squared in absolute value. And then I have to rewrite this. This is equal to x arctangent of x, and don't forget my plus c. Cool, there's my final answer. And I'm worried that maybe I went over the antiderivative of this function too fast. Just make sure that you guys understand where I'm coming from. Really what you can rewrite this as is x times 1 plus x squared all to the negative 1, and then this x turns into the 1/2, and then the antiderivative of anything to the power of negative 1 is natural log of whatever that inside was. On to example 4, our first definite integral. We have 2 homework assignments, like I said before. The first homework assignment is all like example 1, 2, and 3, and then it gets slightly harder. Now you have to plug in things. So we're doing the same thing that we did before, but then we're plugging things in on top of that. I can't take the antiderivative of natural log without using integration by parts. So let's set it up. We need a u and we need a dv. So the u will turn into a du, and the dv will turn into a v. What should we choose where? I know how to take the derivative of the natural log. I don't know how to take the antiderivative of natural log, so I'm going to put natural log here and nothing there. And then from there, the derivative of natural log of x is just 1 over x, and the antiderivative of 1 is x. So again, multiplying this direction for the first piece, so this is going to be equal to x natural log of x, and then it's going to be minus the antiderivative, or the integral of these two together, so antiderivative of x over x dx, and that's really nice. That's really just 1, right? You can cross it out and say that's really just, it goes to 1. So what's the antiderivative of 1? It's just x. So my final answer here is x. Ooh, I haven't been very formal about my bounds, have I? So I can make it formal by doing 1 to e here and 1 to e here. So this is x natural log of x minus, and then antiderivative of 1 again is x, evaluation bar between 1 and e. So now we have to start plugging these things in, and I realize this is getting kind of squished in together, so let me drag these things. Ooh, I don't know if I can, oh, just barely grab all that and move it down there. Cool. So what is that going to be equal to? Well, when I plug in e, that'll be e times natural log of e minus e. So that's the first piece, and then I'm going to subtract my second piece. So when I plug in 1, I'm going to get 1 times natural log of 1 minus 1. And what do we have here? So a few things cancel out. So natural log of e is just 1. Natural log of 1 is 0. Those are two definitions that we should have memorized. If not, you're learning them now. So e times 1 is e. So this is e minus e. That was that first parentheses. And then minus that second parentheses is 0 minus 1. And that simplifies even further to 0 plus 1, or just 1. So this is just 1, which is kind of cool to think about. So the natural log function, I'm done with the lesson, but I'm just kind of going off of a tangent now. You can totally ignore me. I'm just thinking to myself, wow, this is kind of cool, because if I look at the natural log function, it goes like this, and it crosses the x-axis here at 1, and then over here at e, it approaches a height here of 1. So this weird curvy section has an area of exactly 1, which is, I think, interpreting that correctly, which is pretty cool. Yeah, that's all I have for the notes today, which means we don't have a lesson until Thursday. Good luck on the homework. Today is just that lesson, because it's such a long lesson. And then if you want to get all the homework done today, those 2 homework assignments, then you get to just kind of chill for the next few days. I'll check in with you guys again tomorrow, but yeah, I'll see you guys tomorrow. Have a good day.